Hi everybody, and once again welcome to Pankaj's Echelon Tutorials. In this today's session we are going to deal with IBDP topic in physics, and this is the D3 topic, okay, and it has a title called Motion in Electromagnetic Fields, okay. Now this is particularly taught in the 12th grade of the IBDP, not in the 11th grade. So let us get started. And before jumping directly into this particular topic, that is motion in the electromagnetic field. Now, when we talk about electromagnetic field, it's a combination of electric field as well as the magnetic field. Okay. So, but we are not going to directly jump into the motion in the electromagnetic field. Instead, we are going to go stepwise. Okay. First, we are going to study what happens only in the magnetic field. Okay, and then slowly we'll come to this topic, that is motion in the electromagnetic field. So before jumping directly into this motion in the electromagnetic field, this topic, let us have some essential pre-knowledge. Okay, now the essential pre-knowledge will be, we have already studied what is electric field, right, in the previous chapters on the in I think in D2 or D1 we have studied that. So we have studied what is electric field. We know how a force is created in an electric field and what are the properties associated with that force. Okay, all that we have studied separately in the electric field. Now let us study what is a magnetic. See, basically in physics you have three fields that you have to deal with. Okay, one is the gravitational field, second is the electric field, and the third is the magnetic field. So now today we are going to start studying something about the magnetic field. So now let us study what is magnetic field. So this is our topic that we are going to start with. Okay, now electric field we have studied in the past, and it is caused due to some charged particles like a positive charge or a negative charge. Okay, negative charge can be an electron, positive charge can be a proton. Okay, so because of this positive or negative charges, okay, electric field is always produced, that we have studied earlier. Magnetic field is also produced, and let us see what can be the causes. Now electric field cause we know, it is either the positive charge or a negative charge, but in the case of magnetic field, let us see what are the causes. So magnetic field is caused due to two things. Okay, number one, the magnets and the magnetic substances. Now we have studied in our school days, when we used to use the bar magnets, okay, the horseshoe magnet, all these are nothing but magnets. Okay, so these physical magnets, they also produce something called magnetic field. Okay, and that is why, because of this magnetic field, the bar magnet will attract the uh, iron nails towards it. Okay, so this we have studied in our school days. So magnets are one of the very biggest source of magnetic field. So you will always find magnetic field surrounding a magnet. Okay, whether it's a bar magnet or whether it's a horseshoe magnet or whether it's a magnetic compass, whatever. So magnets are one of the source. But later on it was seen that even a current carrying wire or a current carrying conductor, this is very important. This is what we are going to study in this today's session. Okay, so current carrying conductors, or you can say moving charges. See, current carrying conductor is nothing but the charges which are moving in the wire. So whether you call it a current carrying conductor or whether you call it as moving charges, one and the same thing. So because of this moving charges or current carrying conductor also, you will find that a magnetic field is produced. Okay, but remember that the charge at rest do not produce magnetic field. So if you think of a charge, okay, which is not moving, it is stationary, then it is not going to produce any magnetic field. Okay, so that is very important point to note. So only if the charges are moving, okay, that is in the case of electric current, okay, in the flowing in the conductor, such conductors will always produce magnetic field around its vicinity, right? So the magnetic field can be caused due to magnets, and also it can be caused due to current carrying conductor. Now, school days, we have studied a lot about magnetic field produced by the magnets that I have already discussed, okay, during the school days, right? Now, let us see how current carrying conductor produces magnetic field. So, now let us concentrate on what happens or how a magnetic field is produced by a current carrying conductor. Okay. So, it was observed, experimented, okay, it was observed as well as experimented long back, okay, by a scientist called Henry Oersted, okay, and he observed that a current carrying conductor and a magnetic compass, when kept side by side, okay, some deflection was seen in the compass needle, right? Now, when the direction of the current was reversed in the conductor, the deflection was seen to be going in the opposite direction. So these were the two main observations done, seen by Henry Oersted in his experiments. Okay, so what he did, he used a current carrying conductor and some magnetic compass, and he kept both of them side by side. So what he observed is, whenever a current carrying conductor and a magnetic compass were kept side by side, he saw some deflection taking place in the compass needle, okay, indicating that there must be some magnetic field produced by the current carrying conductor. Another big thing that he observed was, when the direction of the current was reversed in the conductor, the deflection was seen to be going in the opposite direction. So the direction of the current will also determine the the direction of the magnetic field. Okay, so these two big observations were done by Henry Oersted in his famous experiment called Oersted experiment. Okay, now this particular experiment and these observations by Henry Oersted made us to jump to a conclusion that a current carrying conductor produces magnetic field in its vicinity. Vicinity means surrounding the magnetic, surrounding the current carrying conductor. Okay, vicinity means in the close area of that conductor. Okay, so current carrying conductor produces a magnetic field in its vicinity. This is a big statement that we can make now. Now, let us concentrate on this diagram. You can see this is indicating a wire which is carrying some current I, and you can see that the current is going in the upward direction. This arrow mark you can see here, it is telling you that the current is going in the upward direction. Say it is going from A to B. This is A, this is B. Okay, so in the conductor the current is flowing from A to B, right? And can you see there's a compass kept over here just next to this current carrying conductor, and you can see some deflection taking place in this compass. Okay, now the moment the current was reversed, the direction of the current was reversed. Now see, in this case, now the current is moving from B to A, so the direction of the current is reversed. So when that was done, it was observed that the deflection in the compass was also in the opposite direction. Here the direction was like this, and here this time the direction is like this. So this is just the opposite direction. Okay, so it was observed that when the direction of the current is reversed, the deflection is also going in the opposite direction. Okay, next thing, so this is a schematic diagram to represent these observations made by Henry Oersted. Now it was also observed that in a current carrying current, now you can see here there's a current going from A to B again. Okay, so there's a current flowing in the conductor. Now this time we are placing just a charge, okay, say a positive or negative, any charge you are placing here, but this charge is at rest, it is not moving. Okay, now what happens, you can see no magnetic effect taking place over here. That means the charge which is at rest nearby to a current carrying conductor does not show any effect. Okay, it is neither being moved, nor it is being attracted, nor it is being repelled. Nothing is happening to this charge which is at rest. This indicates that a current carrying conductor doesn't produce, okay, now this I have written over here, an electric field will produce a force Fe on any charge, whether moving or at rest. Now this we have studied in the previous chapter connected to the electric field. So suppose you have an electric field, okay, a uniform electric field like this, okay, and if you place some charge q, either it's a positive charge or a negative charge, okay, whether you put a positive or negative charge. Now what happens, whether this charge is at rest or it is moving, what happens is this charge is being affected by this electric field. This electric field can be represented by capital E. Now what is the effect that you can see? A force is being applied, which is known as electrostatic force. A force is being applied on the charge, whether it is a positive or a negative charge, and whether it is at rest or in motion, a force is always exerted on this charge, and this force is equal to, okay, it is having a relationship with the electric field. So electric field will be equal to, force will be equal to electric field times the charge. Okay, so this is what we can observe. Okay, so this is what can be seen. Now here, when a current carrying conductor is taken and a charge is placed at rest just next to it, we don't see anything happening. This means that a current carrying conductor therefore does not produce any electric field. Okay, so even though the current is flowing through this conductor, the electric field is not being produced. If at all the electric field was produced in the vicinity of this conductor, this particular charge, whether it is at rest or in motion, it would have been affected by the force according to this. But we cannot see that happening over here. So what we conclude from here is an electric field, electric carrying conductor will never produce any electric field. Okay. Now, suppose you have a current carrying conductor, concentrate here. If you have a current carrying conductor, okay, and now if you take a charge and place it nearby to this current carrying conductor, but this time the charge is not at rest, okay, it is moving. So this is a moving charge, right? It is moving with some velocity, whether it is a uniform velocity, whether it is a non-uniform velocity, whatever, it is just moving. Okay, so when the charge is moving, suppose it is moving in the upward direction, okay, now what is seen, this charge which was moving in the upward direction is getting deflected. Okay, it is getting deflected in some other direction. Okay, so can you see this is the deflection taking place, right? Now this deflection is taking place indicates that there is some force acting on this moving charge. So here we see the presence of some force. Okay, and because there is some force, okay, acting on this moving charge, that means there must be some field created over here. So here we conclude that a moving charge is deflected because some force Fm. Now this Fm is standing for magnetic force. Okay, and I'm saying this Fm because this field is going to be named as a magnetic field. Okay, so some force Fm, which you can call as a magnetic force, is produced because of this current carrying conductor, and it affects only a moving charge. It did not affect a charge which was at rest. So moving charge is affected by this particular current carrying conductor. So we can conclude that a current carrying conductor, okay, produces a magnetic field. Because of this magnetic field, there is a force generated, and that force will make the charge change its direction. Previously it was moving in the upward direction, but now it will get deflected in one particular direction. Its direction will be changing. It's not moving constantly in the upward direction. Okay, it will be deflected. So the deflection is indicating the presence of some force, and the presence of the force is indicating the presence of some field, and this field is nothing but the magnetic field. So we jump to the conclusion that a magnetic field is always generated because of a current carrying conductor, but it will affect only a moving charge, not a charge which is at rest. Okay. Slowly, steadily, we are going to now compare both the fields, the electric and the magnetic field. So electric field is generally represented by E, capital E, and it is a vector quantity that you know very well. So electric field is a vector quantity. Magnetic field is denoted by a capital B, and that is also a vector quantity. That means it has magnitude as well as direction. Okay. So magnetic field is denoted by B, and it is a vector quantity, so it has magnitude as well as direction. Now, electric field is produced by either a positive charge or a negative charge that we have already studied. But in the case of magnetic field, it is produced due to magnets, that is the poles, the north and the south pole of the magnets, and it is also due to the current carrying conductor. So this current carrying conductor, they act as a magnet in short. Okay, so current carrying conductors become a magnet, and because of those magnet, the magnetic field is created. Now let us talk about the units. Okay, now let us talk about the force. Okay, so electric field produces force which acts on a charge at rest as well as in motion. So electric field which is produced, it will affect a charge which is, even if it is on rest, it will be affected, and even if it is moving, it will be affected. Okay, so electric field has that property. But the magnetic field will produce a force which will act only on a moving charge, not on a stationary charge. So this, it produces, means the magnetic field produces force on a moving charge only. It will produce a force on a moving charge only. It is not producing any force on a stationary charge, because a stationary charge is not affected by the force. Okay. Now, units of the electric field. We have studied in the past that the unit of the electric field is Newton per Coulomb, because electric field by definition is electric force divided by the charge. Electric force has a unit of Newton, and the charge has a unit of Coulomb. So you can see that electric field has a unit of Newton per Coulomb. Same way, this magnetic field B will have a unit of something called Newton per ampere meter. Okay, Newton per ampere meter. This is one of the units of magnetic field, and this is the unit in SI system. Okay, in SI system I am talking about the unit. Okay, now this unit, Newton per ampere meter, ampere into meter. Okay, ampere is the unit for current, meter is the unit for the length. Okay, in SI system. So Newton per ampere meter together is called as something called Tesla, T-E-S-L-A, which is denoted by T. So Tesla is a unit for the magnetic field strength or magnetic field intensity. Unit of B, that is the magnetic field, can also be written in terms of Weber per meter square. Okay, Weber per meter square. Now what is Weber? Weber is the unit for a magnetic for a quantity called as magnetic flux. Okay, or you can call it change in flux, change in magnetic flux. Okay, so Weber is a unit for magnetic flux. So magnetic flux, okay, divided by the area is nothing but the magnetic field. Okay, so this is equal to the magnetic field. So B will also have a unit called Weber per meter square. Okay, Weber per meter square. Right, so Weber per meter square is also a unit of magnetic field. So magnetic field can be expressed in Newton per ampere meter, which is also known as Tesla, or it can be also expressed in terms of Weber per meter square. Okay. Okay. Now, this today's session, I'll end up with a short this thing. What we are going to study further. So this was just an introduction of all the terms regarding magnetic field. Now, since you know what is magnetic field or what is magnetic field strength, okay, we should know how to measure it or how to determine it. Okay. Now, because this magnetic field B has some strength, like electric field also has some strength, magnetic field also has some strength. So it is, the strength is, the other name for strength is intensity. So like you have electric field intensity, you have magnetic field intensity. So magnetic strength or magnetic field intensity, representing or denoted by capital B, which is a vector quantity, is given by a law which is known as Biot-Savart's law. Now Biot-Savart's law states that this particular quantity dB. Now can you see this is a vector quantity because I have put an arrow mark on top of this. Okay. So dB is equal to mu 0 upon 4 pi times I multiplied by vector dl cross vector r divided by r cube. So this is a formula, or this is a law which will help you in finding dB. Now let me tell you what is this dB. Okay. And since it is in the vector form, this is known as the vector version. Okay, this is the vector version of your Biot-Savart's law. Okay. Now, if you want to write it as a scalar version, okay, so you will remove this vector sign, the arrow mark from the top. So you'll just write dB. So this is your scalar version. Okay, this is your scalar version. Right. Now scalar version says that dB, that is the magnitude of this magnetic field intensity, is equal to mu 0 upon 4 pi times the current I times the dl times r sine theta, whole thing divided by r cube. And this r and r cube will reduce to, this r from the top will go away, and you will get this final formula for the scalar version. Scalar version, this will be the formula mu 0 upon 4 pi I dl sine theta. This r will cut, and here you will get, instead of r cube, you will get r square. So these are the two big formulas which will help you in determining the magnetic field intensity. But let me tell you, before you get confused, okay, let me tell you what is this. So what I mean to see now, I'll explain you the meaning of these two formulas. Okay, now what is the meaning of this? The meaning of this is, suppose you have a current carrying conductor. Suppose there is a current moving in the upward direction like this. Okay, so you take a small element. Okay, you just take a small element, a small piece of this particular wire. This is a current carrying conductor. Okay. Now you know by now that a current carrying conductor always produces a magnetic field. Okay, so suppose at some point P over here, suppose this is a point P, which is at a distance of, say, R. The distance is how much? R. From this particular small element. Okay, which is represented by dl, vector dl. Let us represent by vector dl. Okay, so this is a small element, vector dl is a small element which is taken as a a small piece of the conducting wire, and from this dl, this is a point P which is at a distance of r, and the distance between this vector dl, suppose this is, now I'll just magnify it and draw, this is vector dl, and suppose this is the point P, and the angle between them is, say, theta. Okay, the angle between the two is theta. This is your r, okay, the distance. Okay, so this dB, vector dB, is nothing but the magnetic field intensity due to a small element dl. Okay, dB is the magnetic field intensity, not due to the entire current carrying conductor. Okay, it is just due to the small element dl of that particular current carrying conductor. So this dB in the vector form can have this formula. So this dB is nothing but the magnetic field intensity due to the small element dl, and this is that formula for dB. It will be equal to mu 0 upon a 4 pi. Now this mu 0 is something which is known as permeability. Like in electric field, you know, we had something called epsilon 0, which was known as permittivity. Okay, epsilon 0 was permittivity, right? This mu 0 is known as permeability of free space. Free space, or you can say vacuum, or you can say air. Okay, this epsilon 0 was permittivity of free space, or you can say vacuum, or you can say air. Okay, so similar to epsilon 0, you have a quantity called mu 0, which is known as permeability, okay, of free space. So that is mu naught divided by 4 pi times this I, which is the current flowing through this small element dl. Okay, so it will be I, and let us take di if you want. Okay, and let it be I only. Okay, times dl cross r. Now this is a cross product. Okay, this is a cross product of dl and r, right? Divided by r cube. R is the distance between this point P and the small element dl. Okay, now this particular formula is nothing but the formula for the magnetic field intensity due to a small element dl. And if you want to find out the magnetic field intensity due to the entire current carrying conductor, you will have to integrate dB. That's it. So when you integrate dB, okay, then you will get something called D. So the magnetic field intensity will be the integration of this small element dB. So dB formula I have discussed. In the vector version, this is the formula. In the scalar version, what will happen? You know, everybody knows that the cross product of two vectors will generate a new vector, okay, which will have sine theta associated with that. Okay, so if you want to convert this into the magnitude, or the magnitude part of this vector dB will be dB equal to, now dl cross r will get reduced to dl into r sine theta. So now the angle will be considered. Okay, so it will be I into dl into r into sine theta divided by r cube, and this r and r cube will get cut, and final formula for the scalar version will be dB is equal to mu 0 upon 4 pi times I times dl times sine theta divided by r square. So these are the two formulas which we are going to use to determine the magnetic field intensity of a small element of the entire current carrying conductor. And when we integrate this dB, we will get the value of the B, that is the magnetic field intensity of the entire conductor. Okay, so this was just an introduction. In the next session, in the next video, I'll come up with some examples, some problems, some numericals, and I'll explain you how to find out this particular magnetic field intensity. Then we are going to discuss about the magnetic field being an vector quantity, how to determine the direction and all that stuff. Okay, so slowly, steadily we'll be moving ahead, and that is how we'll be reaching to the topic called the very much topic of this our session, which was motion in electromagnetic field. So right now we are just talking about the motion in the magnetic field. Okay, and when we combine the electric and the magnetic field, then what will be the motion, what will be the effect on the motion in the electromagnetic field, that we are going to study. Okay, so it's a long way, but we are starting with a very simple topic, which is motion in the magnetic field. So that is what I have started with. So see you in the next video with some more numericals. Okay, till then, bye, take care all of you.